Auzu billahi minash shaitanir rajim. Bismillahir rahmanir rahim. Assalamu alaikum class. This is your teacher Umar Tabrez Shami for the MSc course Advanced Power Electronics semester spring 2020. I pray to Allah for the protection and well-being of all of my students. Today's date is 3rd June 2020. Today we will start with the chapter number 6 of our textbook. The title of our new chapter number 6, is DC to DC converters. In this chapter, power electronic converters for the DC to DC conversion are explained. Along with this, static DC switches with fully controlled semiconductor power switches and forcefully commutated SCR are explained and presented. Further on, we will discuss the single, the two, and the four quadrant step down operation of DC to DC converters. They will be analyzed and we will also discuss applications. In this chapter, the guidelines for device selection are also presented. And as a reminder, my students, it is mandatory for my students to listen to the lectures, and also mandatory book reading is also very mandatory. So let us start with our new chapter. So first article number 6.1, title of the article is static DC switches. Why are they called static? Because they are non-moving. They are all solid state devices. First circuit, figure number 6.21, represents the static DC switch based on a fully controlled semiconductor power switch. This circuit is our normal DC to DC step down converter. The components are one DC power supply represented as VI. The current from the power supply is represented as I or I input. Then we have a switch called switch S. This is our fully controlled semiconductor power switch. Here an IGBT is shown. Then we have a freewheeling diode. We will come to the operation of the freewheeling diode and the importance of the freewheeling diode after we discuss the load. Then after the freewheeling diode, we can see the load. The load can be resistive load, the load can be RL load, or it can be RLC load. The current flowing into the load is represented by I naught or I output. Now, since this is a DC to DC converter, so this means that we can have a variety of loads. For example, in the case of resistive load, we can have a heating system. We can have a resistive heating system where the resistor will represent the heat. We can also have a DC motor connected to the load. The DC motor will be represented by a RL circuit. Now, in the case of resistive load, there will be no trailing current. However, in the case of RL load, the inductor in the load will not reduce the current immediately to zero. There will always be some residual current. So in case we have an RL load and the switch is turned on, then then what will happen, that switch is turned on, then the current flows in this direction as shown in the red line. Now the current flows through the RL load. The inductor stores energy as half Li square, and later when we want to turn off the switch, the current is still flowing. So this current, if we turn off the switch, we have to provide an alternate path for the inductive current to decay to zero, and this path will be provided by our freewheeling diode number D. So when we turn off the switch, at that time the current flows through the load into the diode and decays to zero. So what we have done here is that we have protected the DC-DC converter from sparking. Otherwise, the half Li square energy will produce large voltage and there will be spike, or it will damage the power converter. Okay, so now let us look at the control signals and voltage and current waveforms for the static DC switch. In figure 6.2, the students can look at 5 various waveforms that are all related to the fully controlled semiconductor power switch DC-DC converter shown in figure 6.1. So first waveform is the control signal. It is written G. G represents the gate, that is the gate voltage supplied to the switch S. The switch S has 3 terminals. One is the drain, one is the source, and one is the gate. The gate is the control signal. When we provide a large voltage, the gate will turn on, and when we supply 0 volt, the gate will turn off. So the first waveform represents the gate signal being supplied to the switch S. It is the controlling signal. The second waveform is the output, V out. The third waveform is the I out. The fourth waveform is the II, or the I input. And the fifth waveform is ID. This is ID. The current in the freewheeling diode is the current ID. We are assuming that the load is a RL circuit. We are assuming that the load is RL circuit. For example, we are using a DC motor connected as the load. Now let us look at the gate signal G. The gate signal G is on, that is it is at a certain voltage above 0 volt. It is at a large voltage with respect to 0 volt, so it is a turn on signal, and this turn on signal remains high voltage for a certain period of time. From 0 to this time the gate is turned on, and from this time to one complete cycle we keep the switch off. We can keep the switch off by applying 0 volt between the gate and source. When we apply high voltage between gate and source, the switch turns on. When we apply 0 volt across the gate and source, the switch turns off. As the switch turns on from 0 to this time, the switch provides a short circuit between the input voltage and the output voltage. Therefore, in the second graph, V out, the output voltage is essentially equal to the input voltage. The output voltage is essentially equal to the input voltage, and this output voltage will remain equal to input voltage as long as the switch remains turned on. As long as the switch remains turned on. Therefore, V out is represented by this bold line, and this bold line has a amplitude equal to V in. Okay. And when the gate signal is removed or when the gate signal is turned off, the output voltage is also reduced to 0, because now the switch is open and there is no voltage being supplied to the load, and hence we get a 0 volt. This is the completion of one cycle on and off. Okay, now we will come to the third graph, that is the I output, I naught. When we supply a voltage across the load, since the load is connected, therefore a current will start to flow. This current will remain constant because the load is constant. This current will remain a straight line as long as the switch is turned on. And then we can observe a very interesting activity when the switch is turned off. Then here is a decaying current. This current comes to 0 after a certain period of time. This is the current. This is due to the inductive component in the load. And we will discuss this in the freewheeling diode current. Right. Now we come to the fourth waveform, that is the I input. When the switch is turned on, the source supplies the current to the load. The source supplies current to the load, and the load current and the input current are both equal and same in wave shape and same in magnitude. So we can see that as long as the switch is turned on, the input current, the source supplies the input current equal to the load current also. But when we turn off the switch, the input current suddenly reduces to 0, because at this time the switch is now open. The current cannot enter into the load current. However, we must not forget that there is a trailing current, inductive current, due to the inductive component of the load. And as an engineer, we have to provide an alternate path. The engineer, the designer, has to provide an alternate path for this decaying current. The engineer will take care beforehand and have an alternate path available, and this alternate path is provided by our diode D. So this brings us to the fifth waveform, that is ID. ID represents the diode current, and this diode current will only flow momentarily for a very small period of time, and this diode current will be active when the switch S is turned off. The switch S is open circuit, but there is inductive current in the load, and this inductive current will now pass this inductive current will now pass through the diode, freewheeling diode, and eventually, since there is no power supply, the energy in the inductor will be reduced, will be lost, and this current will gradually come to 0. This circuit 6.1 is our normal DC-DC step-down converter, also called as the buck-type converter. The output voltage is a function of input voltage and the duty ratio. Duty ratio M is equal to T on divided by T on plus T off. Duty ratio. So output voltage is the multiplication of V in multiplied by T on divided by T on plus T off. This means that we can vary the output voltage. We can vary. This is, as my students, they have already studied this in undergraduate courses, that output voltage is variable from 0 volt to V in the case of step down DC-DC converter, and the function is V out is equal to V in multiply by bracket T on divided by T on plus T off bracket closed. Yeah. So yes. However, we have to visualize, or we have to understand that the switch S is a IGBT in this case, as case shown in 6.1, figure 6.1. It can be IGBT, it can be MOSFET, or it can be a simple BJT, where when we supply gate signal, current flows. When we remove the gate signal, when we turn off the gate signal, the switch turns into open circuit. However, this is not the case if the switch was an SCR. If the switch was an SCR, then we need a separate turn off circuit to turn off the SCR. And this brings us to our next slide. This is the same circuit. However, this time we are not using IGBT. Figure number 6.3 is also a DC-DC step-down converter. However, the power electronic switch is not IGBT, it is not BJT, it is not a MOSFET, it is a SCR. Why are we using SCR? Because SCR, they have high current handling capacity. So in the case the load demands much current, then MOSFETs or IGBTs might not be feasible, and we will be compelled, or it will be essential for us to use SCRs. Now there is a problem with SCR, that the SCR, in SCR there are separate technique to turn on the SCR, and there is separate technique to turn off the SCR. Therefore, as shown in figure 6.3, the circuit, although it is simple buck-buck, is a simple buck converter, but there is a the SCR, with the SCR there is a complicated or complex network, electric network shown. For the SCR, we can turn on the SCR using a gate current, and to turn off the SCR, we have to ensure that the holding current is less, that the current, we have to ensure that the current flowing through the thyristor is less than the holding current. So let us revise this concept of turning off and turning on the SCR. In figure 2.6, this is a revision. This figure has been taken from chapter number 2 of our same book. The figure number is figure 2.6. Title of the figure, caption of the figure is voltage current characteristics of the SCR. The SCR operates in either the first quadrant or in the third quadrant. Now, here is the VI characteristics. On the x-axis is the voltage across the SCR, and on the y-axis is the current of the SCR. Now this is IH and IL. IH is the represents the holding current, and IL represents the latching current. IH is the holding current, IL is the latching current. Holding current indicates, or holding current tells us, if we want to turn off the SCR, then we must ensure that the current flowing through the SCR must be less than the holding current, IH. This IH information can be found from the manufacturer sheet, manufacturer data sheet of the SCR. IL, the latching current, tells us that if we want to make a continuous current to flow through the SCR, then the current flowing through the SCR must be larger than the latching current. And this data, or the value of IL, is also provided in the manufacturer data sheet of the SCR. So to turn off the SCR, we have to ensure that the current flowing through the SCR is less than the holding current. And for this turn off process, we are using additional circuit, which includes capacitor, thyristor T2, inductor L and D2. This additional network is used only to turn off the SCR. And to turn on the SCR, there is a separate driver circuit, which is not shown in this diagram, as we have done this in a previous lecture. So to turn on the SCR, we need a driver circuit. The driver circuit will provide enough gate current, IG, to turn on the SCR. However, the driver circuit will not be discussed in this. We will only discuss the turn off procedure of the SCR. So in this slide, we did a revision of voltage current characteristics of the SCR, and we refreshed our memories that to turn off the SCR, we need to reduce the thyristor current less than the holding current. And in the next slide, we will discuss how the SCR turns off itself. Right, so now in the following slide, we will discuss the turn off procedure of thyristor in the SCR based static DC switch. So this is our main circuit. The circuit consists of input voltage Vi, main thyristor T1, then freewheeling diode D1, load, and then the force commutating turn off circuitry consisting of capacitor C, thyristor T2, inductance L, and reverse connected diode D2. So in this part, we will discuss how thyristor T1 is turned on and how it is turned off. Our major focus will be on how thyristor T1 will turn off. This circuit that you see is your normal DC-DC step-down converter. We are using SCRs. So thyristor T1 is our main current or our main power electronic switch. We will turn off and turn off. We will turn off or turn on the we will control the output voltage using turn on or turn off of T1. Now to turn on T1, we need a drive circuit. The driver circuit is not shown, however, we have discussed driver circuits in chapter number 2, so in the class, so I will not repeat them over here. However, the turn off procedure is very interesting. We need additional circuitry consisting of capacitor C, thyristor T2, inductance L, and diode D2. So how do we turn off current? How do we turn off T1? The answer lies in the characteristic, the VI characteristic of the SCR. That is, to turn off the SCR, we must ensure that the main current flowing through the SCR is less than the holding current. That is the only technique we have to turn off the SCR. Now we will apply this technique in the given circuit. That is, first, when the thyristor is on, at that time our main current flows through T1. This is when the thyristor is turned on. The main current flows from the power supply through T1 and into the load. And how do we turn off the SCR? We turn off the SCR by reducing the current through the SCR less than the holding current. This will be done if we bypass the main current. If we bypass the main current into the load. When we bypass the main current through T2, then current in T1 will be less than, or it will be zero, it will be less than the holding current, therefore T1 will turn off. This is the concept. This is called forced commutation, and this circuit consisting of capacitor C, inductor L, T2 and D2. This is our forced commutating circuitry. Now let us see how this circuit works. How this circuit works. The circuit consisting of capacitor and inductor and T2. Then when we are bypassing, while we are bypassing, main current is flowing through T2. Then a question will rise, how will we turn off T2? Because T2 is also a thyristor just like T1. How do we turn off T2 when we want to turn off T1? Then we have a very simple answer, ठीक है? That is, bypass T1 and make the current flow through T2. Fine, that's good. We have bypassed T1, therefore the current in T1 comes to zero, T1 is turned off. But now, since the main current is now flowing through T2, how will we turn off T2, or who will turn off T2? Because T2, just like T1, is also an SCR. To turn off T2, we have to apply the same concept, that is to make the current in T2 less than the holding current of thyristor T2. So how do we? So should we use another commutating circuitry? Then this series will continue. Now the answer lies in the inductance and capacitance and D2 circuit. If we look close into circuit, the capacitance C, the inductance L form a second order system. We design capacitor C and inductance L so that we get a underdamped response. This is very important. When we get an underdamped response, we will get underdamped isolations. The underdamped isolation is that the current in T2 will be oscillating. It will be sine-like. The current will be oscillating. We have designed C and L to form an underdamped oscillating current. This current will follow a sine wave, and when this sine wave current passes through 0 ampere, T2 will turn off naturally. Okay? So we don't need an extra commutating circuit to turn off T2 because we have designed the commutating circuit to be a second order system, and we choose values of C and L so that we get underdamped oscillations. These underdamped oscillations ensure that the current in T2 is not constant. It is a sine line, and this sign will a time will come when this sign will cross 0 ampere. At 0 ampere, the current in T2 becomes less than the holding current of T2. Therefore, T2 follows a natural turn-off process, or which we call natural commutation. So now we come to the wave shapes of how the circuit will work. Right. So here in this waveforms, these waveforms are not taken from your textbook. The waveforms are also available in the textbook, but I found that this waveform are much more easier to follow, and they can clear much more concepts. So these waveforms you will find in the handout that will be available, inshallah. So let us look at the components waveforms available in this diagram. First component is IG1. This is the gate signal of thyristor T1. Gate signal of thyristor T1 is called G1, and since thyristor is a current controlling device, therefore we need gate currents. So IG1. This is the gate signal for thyristor T1, and second we have the gate signal for thyristor 2, and it is called IG2. Then we have IC. IC represents the capacitor current. Then we have IT1. IT1 is the current in capacitor T. IT1 is the current in thyristor T1. Then we have VC, capacitor voltage, and then we have VT1, voltage of the thyristor T1. So when we want to turn on T1, this is T1. When we want to turn on T1, that is when we want to allow current to flow from the main T1, what we can do is we simply turn on IG1. We apply current to gate of T1. As a result, T1 is turned on and main current flows through the source through T1 into the load. And we can see this, that IT1 is now conductive. Now this sign like is due sign this curve riding over constant current. This is our constant current, and a curve is riding over. So it is due to the fact that it is output current plus IP. IP is over here, that is the capacitor transient current. When we must not forget that the capacitor behaves like a short circuit in transient time. So curve, this curve that you see at IC, this curve is due to the transient current in the capacitor. So when we turn on IG1, current flows through IG1, and momentarily there is a small current due to the capacitor transient, and a major part of the current is due to the load current called I out, over here, I out, and this is I out over here. The capacitor, when Ig1 is turned on, the capacitor will reverse in its voltage polarity. And when we turn on Ig1, voltage across the thyristor T1 will be zero because it is now a short circuit. It is now a short circuit. This thyristor T1 can continue to turn on for infinite time until we provide gate signal to T2. Now, now let us assume that we want to turn off. Now let us assume that we want to turn off um, thyristor T1. What should we do? To turn off thyristor T1, we have to turn on thyristor T2. This is thyristor T2. So to turn on thyristor T2, we supply a gate signal at gate of T2. When this gate signal applies, when we apply gate signal, thyristor T2, thyristor T2 is short circuit, and capacitor, it enters into transient, it becomes a short circuit, and therefore it allows the main current to flow through the capacitor through T2 into the load. So when we turn on T2, what happens is that main current flows through the capacitor through T2 and then into the load. Hence, the main current is now bypassed from T1, and this we can see over here in the graph of IT1. This is graph of IT1, that now the current through T1 is now almost zero, which is now less than the holding current. So technically we have accomplished the bypass. Okay. So now remains the fact that how do we turn off T2? This is very important. We have turned on T2. As a result, current was bypassed from T1, current now passing from T2. Second question, how do we turn off T2? We will turn off T2 by the choosing proper values of C and L so that they form a second order system where the current crosses 0 amperes at a certain time and T2 is naturally commutated so yes, so this complex network consisting of capacitor C, thyristor T2, inductor L, and T2, they they are one reason why SCRs are not preferred over when once IGBTs or MOSFETs or BJTs are available, because it is tedious, it is difficult to turn off the SCR. We need extra circuitry. These extra circuitry will make our whole circuit much more complex. Right, a small discussion of how small discussion of second order, that we can observe that when T2 is turned on, we have a second, we got the bypass current. Now let us look at the voltage across capacitor here. The voltage across capacitor is now crossing 0 volt due to its underdamped oscillation characteristics. We can see that the voltage is now crossing 0 volt, and this is the reason why We don't need a separate circuit to turn off T2 because T2 will experience natural turn off. And in the last waveform, voltage across thyristor T1, the voltage across thyristor T1 will experience a reversal, and when the current stops, the main current stops, the voltage across T1 will now be equal to input voltage, source voltage Vs. So this is the procedure how the SCR they turn off. Okay? Right, so this now brings us to the end of our first half of this chapter. We will stop over here, and in the second half, in my new lecture video, we will discuss step down converters working in all four quadrants and step up converters. Okay. So thank you very much for listening. Thank you very much for your attention. अपना ख्याल रखें, हम सब के लिए दुआ करें। बहुत शुक्रिया। अस्सलाम वालेकुम।